Okay, so let's talk about rates. Rates of change. Yeah, I mean, you study this in math class. It's not going to be mind-bending or anything like that, but we're just going to learn how delta notation applies to a rate of change, okay? So rate of change is just simply that, something, some value that changes with the passing of time. And first rate of change we're going to look at is a rate of change in position, okay? So to do that, let's draw ourselves a number line to kind of keep track of what's going on here. Uh-oh, it's not a straight line. Let's try that again. There we go. Okay. Okay, so I'm just going to make myself a little simple number line here. And we're going to imagine an object moving around on the number line, okay? So, I mean, we can make it a little person if you want. Let's see, little purple guy. Okay, so we're going to say that the initial position of the person is here, okay? And that value, if you look, is -1. And we'll say we're talking in the unit meters, -1. And let's say this person moves over to here. All right, and we'll say that their final position is 1, 2, 3, 4. Okay, so the first thing we're going to ask is, well, what is their delta? What is their delta D? What is their displacement? So if you remember from last class, delta D, the change in position, which is known as displacement, is their final position minus their initial position. So we've got 4 minus -1, which equals 5 meters. So delta D in this case is 5 meters. Okay, so this is not a rate yet. Okay, all that we've discovered here is that their displacement is 5 meters. Where rate comes in is when we look at how long it took them to go from here to here. So let's think of two different options. Actually, let's talk about two different people. So let's say this person's friend also does the same motion. Okay, and then we'll say that it takes them 2 different times to do this. So let's say here that the initial time, we'll call it Ti, equals 0 seconds. All right, Ti equals 0 seconds. What I'm saying here is the initial time is 0. So the stopwatch is at 0. When they start moving, we click the stopwatch on and we start seeing how long it takes the person to go. And let's say that this person gets to here when the clock gets to 5 seconds. And let's say that this person gets to here when the clock reaches 10 seconds. Okay? So the first question when thinking about this is, which one of these two is faster? Who's faster, purple person or light blue person? Light blue person, right? And just to indicate this, let's make this one into a turtle, just for fun. Which one's faster? Who's faster? The purple person's faster, right? Because it took him only 5 seconds to go the distance, and it took this one 10 seconds to go the distance, right? So it took this turtle took twice as long to get to this point here, right, as the person did. So the turtle is slower, right? The turtle's slower, the person's faster. Okay, so here's a couple of things to think about, right? We can look at this in terms of the speeds of the objects, okay? But seeing as how we're indicating, and there's a possibility they could go the other way, we're going to talk about it in terms of velocities of the object. So what is velocity? The concept of velocity is this. Like speed, it is looking at essentially a change in something, right? So speed is, I guess, how fast you are passing a certain distance, right? Like 100 kilometers every hour, right? That's how fast you're going. 120 kilometers every hour, you're covering a bit more kilometers every hour. With velocity, it's the same idea. It's just that there's a direction attached. So both of these objects are moving positively. we could try and we could change it to negatively in a moment here, but velocity is the rate of change in position. Okay, and we define the change in position, right? We define the change in position as what? What do we call a change in position? A displacement, right? A displacement. So what we're really talking about is the rate of displacement, I guess, at the end of the day, okay? And the way that we're going to write that is simply this. We're going to say that velocity is always going to be found as change in position, delta D, or displacement, versus the change in time, how much time it took to do that, right? So we look up here. Let's see what we have. We have a delta T, a change in time of 5 seconds, right? 5 minus 0, TF minus TF, 5 minus 0 is 5 seconds. It's nice and easy when you start at 0, right? Because your rate of change, or your delta T, I guess, will always be equal to just whatever your final number is. Sometimes this won't start at 0, but mostly it does. And then your delta T here is 10 seconds. And your delta D here is the same as it was above, which is 5 meters, okay? So let's talk about the velocity. And velocity is a vector value. So sometimes you might see a little arrow on top of it just to say that it's a vector. I don't really require that, but just be aware. Sometimes you'll see a little arrow. That's all it means. It just means we're talking about a vector, which means it could be negative. So let's talk about for the person. So I'm going to put a little subscript, meaning we mean the velocity of the person. To do the velocity of the person, we take the delta D, which is df, minus di, and we divide it by the time that it took, tf over ti. So in this case, we've already figured out that's 5 meters, and it took this person 5 seconds. So what we get is 5 meters over 5 seconds, and we can reduce this down to simply 1 meter every second, which we learned is nicer to write like this. 1 meter per second. Okay, we'll analyze this in just a second. Just to kind of reinforce this idea, I think you can already see where we're going to go, but let's just do the turtle really fast. The velocity of the turtle is the change in change in position of the turtle over the time it took the turtle to do the change. So for the turtle, it still went 5 meters. However, it took it 10 seconds. So it's 0.5 meters per second. So the turtle is moving half the velocity of the person, okay? Now, something I want you to realize, these could be negative values. There'd be no problem with writing these as negative values, right? All it would mean, though, is that the people or the objects are moving the other way, okay? So let's try one. I'll give you one to try, and I'll make sure that it's a negative value here, okay? So we'll draw a little number line. We'll put some points on the number line. Okay, that. All right, 1, 2, 3, 4 meters, and 1, 2, 3, 4, negative 4 meters. Let's make a, what kind of animal do you want it to be? How about a giraffe? A turkey? Maybe I could draw a turkey. Let's try a turkey. What is a turkey? A turkey looks like this. Yeah, it might be. Yeah, I think like Black Friday is coming up or something. No, it's not a peacock. It's a turkey. It's got a little gobbler there. It's a turkey, man. Okay. So let's try to make this slightly more difficult. Let's make it slightly more difficult. Okay. So initial position of this turkey is 3 meters. And the turkey is going to like gobble walk here. But then he's going to gobble walk back here. And then he's going to gobble walk all the way over here. Oh yeah, he's a very confused turkey. That's true. Okay, there's his eye. And I'm not going to draw, I don't even have to draw the turkey again. I can just like copy him. Oh, maybe I can't copy him. Turkey, let me copy you. Okay, we figured out how to copy the turkey. So let's imagine we can actually like make it happen. The turkey goes like gobble 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 gobble. Oh, it is recording. Whoops. Oh well. Sorry, having a little technical difficulty here. So the final position of the turkey is -3. So here's a couple of interesting things that happen with this. So the first thing is velocity does not care that the turkey went backwards. Velocity doesn't care, right? Because if you look at what we said velocity was, well, velocity is just I guess you could say the average rate of change for this turkey. So it's not like smart enough to actually know that the turkey went back and forth. So if we look at it, what it's just going to take in here is delta D, okay, the displacement, which in this case is -6, and the time that it took. So let's say now, you're just looking at the clock, and you see that this turkey started to walk at like 9 a.m., and that the turkey ended up over here at like 9 minutes and 9:01, let's say. So it took it 1 minute. Okay, so it took it 1 minute. So we're gonna have to like be a little more careful with how we deal with this now. Okay. So if we're looking at velocity, we essentially are going to ignore the fact that the turkey gobbled his way this way, then he gobbled on back, and then gobbled on down here. All right. So we're going to treat this correctly in terms of just a vector, and then we'll talk about what if we deal with speed of the turkey versus the velocity of the turkey. Okay, so let's just see what velocity will give us here. So the average rate of change in the turkey's motion. Okay, so the average rate of change. So this just is simply going to take his final turkey position, subtract his initial turkey position, and then time. Okay, well, we're people here, and we're smarter than math, so we realize that, the turkey's moving in meters. He's got a minute here. We want to talk in terms of meters per second. So how many seconds of time are we talking about here? Yes, 60 seconds. This motion happens over 60 seconds. Okay. All right. So we've got a final, a -3, subtract an initial 3, and that all happens over 60 seconds. So what we have here is we have -6 meters, right, which is the displacement. It's not the total distance he traveled, it's just his displacement, -6 meters, right? It's how far out of place he is over 60 seconds, and that should give you -0.1 meters per second. Okay, so there is the turkey's velocity. And we had to be clever with it, right? We didn't just take the formula blindly and try to jam numbers into it. We realize if we're talking about a minute, we really mean 60 seconds. We kind of want to probably stay in the units of meters per second. It's pretty conventional. Those are our MKS base units. Although sometimes we talk about kilometers per hour. It doesn't make sense if a turkey's only walking 6 meters to talk about kilometers per hour. So this is a pretty sensible approach. Okay, now does this mean that the turkey for sure actually ever traveled at 0.1 meter per second? Did he actually ever do that? And the answer to that is no, right? It's actually impossible for him to really, it's maybe for a split second in there, he traveled at 0.1 meter per second. But what we're really talking about here is what we like to call the average velocity, okay? So the average velocity simply looks at your input values and spits this out at the end. Would you say that that's a very useful unit for a case like this? Is that really all that useful? It's not really that useful, right? In this sense, where we're looking at a turkey moving back and forth, we want to know how fast he actually went. This doesn't really describe that. But what it does tell us, though, is if we only had this amount of information at where the turkey started, if we put in a time, we know he'd be here at the end of it, right? That's kind of what we're saying. It's as if he traveled constantly at 0.1 meters per second to the left. So if there were another turkey that is like our theoretical turkey, he's just walking along at 0.1 meters every second and he ends up over here. Meanwhile, this turkey like scurries around. but the end result is the same. Both turkeys are here at the end of it. Okay, so now let's take this concept and let's just talk about speed, the speed of the turkey. Well, speed is distance over time, and we're going to see here that speed of this turkey is actually different. This is how much time it took. So it still took 60 seconds, right? This motion still went over 60 seconds. However, the turkey went 1, 2, 3, 4, 5, 6, 7, 8. He actually went 8 meters total in that amount of time, right? Because distance ignores whether he was going left or right, right? Distance just ignores that. It just keeps counting up, right? Wherever the turkey goes, his distance gets farther and farther. So we get 0.13 meters per second. Notice no negative, right? We're talking about a speed. Speed does not care about direction. It's not a vector value. It's just scalar, okay? So for the same motion, we can actually pull out 2 different values. Which one we use and when we use it is up to the person using it, right? These are just 2 tools. You have to realize the difference and when it's appropriate to use each one, okay? So these are both rates in a sense, all right? Velocity is kind of, I don't know, it's sort of where we spend most of our time in physics. Although in everyday life, it often makes more sense to actually be talking about speed, right? This is kind of like, I don't know, I guess it tells you the turkey's moving left, but doesn't really describe his actual, like, real motion, whereas this kind of does, but doesn't really tell you what direction he's going in. So one of these 2 tools will be right for the particular situation that you're using it in. It's up to you to figure that out, okay? So in general, are there other rates? Yes, there are, okay? So the rate we're talking about specifically is velocity, but there's lots of other rates out there, right? So for instance, let's just fire a few out here. Let's say the temperature drops 10 degrees in 1 hour. We might say that the rate is, 10 degrees, negative 10 degrees per hour, right? There's a rate. Let's say you get paid like $12 every hour you work. Well, your rate of pay is $12 per hour. That's a rate, right? Your pay rate. What else can we think of that's a rate? Really anything that you're measuring versus time, right? Cost to park usually is a rate, like $2 an hour. What else? Passing rate, right? Number of students who pass a course. For this course, it's usually about 90% passing rate. That's not bad, okay? I imagine for you guys, because you are so good, we should be able to get a 100% passing rate, I think. All right? So there we go. That's what rates are, and we'll leave it at that for now. Later, we're going to get more complicated. We're going to talk about, well, what happens if, the turkey starts to speed up, right? Then the velocity is actually changing as well. So then we have a rate of change in a rate of change. Yeah, and then it gets more fun, more complicated. All right, but we'll leave it there for now.